Hello, I'm James Floyd. We're going to work a pendulum problem dealing with conservation of energy. This is the problem we're going to do. This pendulum here has a length of 1.25 meters. Its bob, which effectively has all the mass, has a speed v sub o when the cord makes an angle of 40 degrees with the vertical. What is the speed of the bob when it is in its lowest position if v sub o is 8.00 meters per second? What is the least value that v sub o can have if the pendulum is to swing down and then up to the horizontal position and to the vertical position with the cord remaining straight? Do the answers to B and C increase or decrease or remain the same if theta is increased by a few degrees? We'll take one part at a time. Okay, this is the setup we have. The bob is in this position with an initial velocity of 8.00 meters per second. The length of this bob, L, is given as 1.25 meters. And we need the height. This bob is up from this position. This will be the height. If you look at this triangle, you see that this side is L cosine of theta, which is 40 degrees. So if we take the cosine L minus L cosine of theta, will give us this height. So let's do that. So L, which is 1.25, minus L, which is 1.25, cosine 40 degrees is equal 0.292 meters. This is the height we want. And this will allow us to calculate the velocity at the lowest point of this pendulum. So we'll start off. mgh initial plus kinetic energy initial is equal potential energy final plus kinetic energy final. Well, the initial height is 0.292 meters times the mass, m mass, times g. The initial velocity, 8 meters per second, will give us kinetic energy of 1/2 times the mass times 8 squared. mgh final, that's at the lowest point here, and that will equal 0. And then we have the kinetic energy final, and that is what we're looking for. So So 1/2 mv squared. We notice all the masses will cancel. So we can cancel that mass, cancel this mass, and we can cancel this mass. And we have these 1/2. Well, that's nice. Why don't we just go 1/2 times this and double this, which will be 19.6 plus 1/2 h squared plus 1/2 v squared. Since we doubled this, we can cancel all the 1/2s, just to clean it up a little. And we have this should be equal from here, equals 1/2 v squared. Now, this whole thing, v, is going to equal square root .292 times 19.6, that's the height, plus h squared, which is 64. And that's equal square root of 69.72, which equal 8.35 meters per second. And that's our answer. Okay, part B. We want to know, what is the least value of BCO can have if the pendulum is to swing down and then up B to a horizontal position and to a vertical position with the cord remaining straight. So let's start with the horizontal position first. Well, mgh initial, which is the initial potential energy, plus 1/2 mv squared initial, that's what we're looking for, is equal to mgh final plus 1/2 mv squared final. Well, this is our pivot position. And at this position, we're going to swing from where this is 40 degrees, still 40 degrees, all the way down to the lowest position, up to the horizontal position. So this is the final position, and it will be still at this position momentarily. This is what we want to look at. So I said mgh final is equal 0. That's not true. So mgh final plus 1/2 mv squared. The final velocity, in this case, is going to be 0. And we're looking for the initial velocity, and we have a initial height. So we can cancel all the masses since we have them everywhere. So we have 1/2 v squared initial is going to equal g times the height final minus g times the height initial. So that is v squared initial is going to equal 2. We take that 1/2 on the other side. We see g is coming with both of these, so we'll take that out, g. And we're going to have the height final minus the height initial. So v, what we're looking for, vi, v sub o, doesn't matter what you call it, is going to equal 2 times 9.8. Well, h final, what is that? That's L. That's the length of the pendulum, which is 1.25. And h initial, we figured that out a little while ago. So h initial is equal to 0.292 minus 2.92, and that was a square, so this is the square root. So v is going to equal, so v is going to equal 2 times 9.8 is 19.6 times 1.25 minus 0.292. And that's equal to 0.958. So V is equal to 4.33 meters per second. In part C, we want to know if the bob goes all the way through this to this position. From here is the original potential energy position. So we go mgh initial plus 1/2 mv squared, that's initial, is equal to 1/2 mv squared, that's final, plus mgh final. All the m's cancel. So we're left with GH initial, which is L minus L cosine theta, that's the length, times G initial plus 1/2 mv initial squared, that's what we're looking for, is equal to 1/2 v square final plus G, and H is the distance from here to here. This is the way you can get it mathematically, which is 2L. Solving for this, 1/2 mv squared initial is going to equal, no m's, the m's have canceled, so get rid of that real quick. 1/2 v squared initial is equal to minus G, take this on the other side, L minus L cosine theta plus 1/2 v squared final plus 2GL. Now the problem states that when we get the bob in this position, the rope is to remain taut. So for that to happen, this must equal mg. So mg, that's this rope here, is equal to 1/2 mv squared over r, which would be L in our case. If we were to bring this L over here, we'd have L mg is equal to m v squared. There was a 1/2 up here. That was a mistake. Earlier, I erased that. So when you're looking at this, you see that if I put a 1/2 mv squared here, I'd have kinetic energy. Well, if I can put a 1/2 on this side, I can also put a 1/2 here. So let's just block this off so it won't. So 1/2 L mg is equal to 1/2 mv v squared. We're going to substitute this with L into this expression right here. So we have 1/2 VI initial square, what we're looking for, is equal to, well, we can take this minus in here and kind of change this around and make it look a little bit better, is G times L cosine theta minus L plus the expression in terms of L. The G's, the M's cancel, just as for the original that I put it in there. So I'd have 1/2 LG plus 2GL. So V squared is going to equal to 2 times this whole thing. G L cosine theta minus L plus, we can take the L's out, we can take the G's out, and we have 2 plus a 1/2, and we'll get 5/2. So V is equal to the square root of 2 times 9.8 times we can take the L's out, which is 1.25 cosine 40 minus 1 plus 1.25 times 9.8 times 5/2. And when you do all this math, you'll get V is equal to 7.35 meters per second. That's V initial. And that's the V required for this bob to be in a vertical position. It's still going to move through that position. That's how the rope stays taut. That's why we use this MG portion here to bob just hanging, knowing that for this rope to stay taut, it must equal MG. So MG, M, B squared over L, that's acceleration when something's moving in a circle. Then we just solve, putting L on this side, and we saw that L, MG, is equal MV squared. And that's where I got the idea, or I didn't really originally get the idea, but anyway, 1/2 L, MG equals 1/2 mv squared. And we just substituted that into this expression. And then we did this math, which we've already went over. And B initial, 7.35. So that solves that portion. Now part D, it asks, do the answers to B and C increase or decrease or remain the same if theta is increased by a few degrees? So what they're asking is that if I were to take theta, which is 40 degrees, and increase it, just say, to 10 more degrees to 50 degrees, would the velocity increase or decrease? So let's just look at that. So the cosine of 40 degrees is 0.766. The cosine of 50 degrees is 0.642. So you go back, look at your formula, and you can see that if I were to increase this, say to 50 degrees, 0.642, the velocity would increase because the cosine of 40 degrees is more than the cosine of 50 degrees. So the velocity would increase in part C. Then it asks, in part B, would it also increase? Well, I didn't have this down here before, but this expression here is 0.292. And we got it from this expression here, 1.25 times 1 minus the cosine of theta. This is L. I showed you this earlier in the video. We have this minus. If we distribute this minus through this equation, we'd have 2 times 9.8 times, not times, 1.25, and if we distribute this minus, we'd have a plus 1.25 times minus 1 plus cosine of theta. Now you clearly can see the same thing would happen. If I increase theta, the function would go down or decrease, which would mean that I'd have a decrease in my initial velocity. So in both cases, if I increase theta for A or B, the velocity would decrease.